Hello, welcome back. So, I hope with the previous 19 lectures you got some idea about modeling transport phenomena of rigid particles and viscous drops. And if you recall, we discussed in brief singular solutions of Stokes equations. Okay. So, it is slightly difficult to follow, but today we are going to discuss some applications, in particular dealing with singular representation of Stokes flow, and then few other applications. So, as I promised, when we are discussing singular solutions, I briefly mentioned modeling transport of some microorganisms or particles like motility of sperm, etc. So, they are very difficult. So, the reason being their aspect ratios are very nasty. Okay. So, you have some head like structure and then long tail. So, traditional numerical methods do not give. Okay. So, let us see in brief some applications and then maybe how the singular solution can be a very useful tool. Okay. So, typically microfluidic environment contains flow inside microchannels, capillaries like arteries, blood flow inside endothelial glycocalyx and some mechanical machines. And other microparticles are like motility of bacteria, microorganisms and sperm, and we have discussed viscous drops and bubbles and a lot of applications in chemical and bioreactors. So, I am sure with the with this subject, when you have done, so you can pick up any of the problems ranging from these. Okay. So, followed by the colloid suspensions and electroosmosis, etc. Right. So, one application that I would like to bring to your notice is modeling motility of sperm. Okay. So, the group of John Blake and D.J. Smith, they have contributed a lot. Okay. So, typically, so this is an experiment and this is the simulation. So, this is experiments are in collaboration with medical community. Okay. So, this is a medical person. So, you see the sperms, they have head and then long tails. Okay. So, hence the aspect ratio is very nasty. So, if you use any traditional numerical method, so you will not get good accuracy. Okay. And on the other hand, so modeling cilia beating. Okay. So, these are like cylindrical cilium and this is ellipsoidal cilium, and when they are in a fluid, so they bend and then collection of cilia produces beating. Okay. So, again from the same group. Okay. This is the reference. So, how one would model? So, this metaconal wave has to be modeled. So, in order to understand that, so individual cilia and then collection of cilia, how the corresponding flow field is generated by the cilia has been discussed by the same group. Okay. So, now the issue is what are the challenges in modeling such things? As I indicated, the aspect ratio do not lead to accurate results using various numerical techniques. Therefore, singularity method is best suited. Okay. So, what is the great about the singularity method? So, as I mentioned, so the technique is as follows. You have a head and then long the tail. So, therefore, what happens if you discretize? So, this domain is like 3 dimensions, let us say, and then this is whether 1D or 2D. So, that one has to really get an idea. Okay. So, how one would model this? So, as I mentioned, this is using singularity method. Okay. So, when you say singularity method, what one would do is they distribute singularities, okay, and then get. So, this is distribution of singularities. Then from here you reduce and obtain boundary value problem, which involves an integral equation, which typically called boundary integral. Okay. Of course, this is itself is a vast subject. So, I am not going into the details, but a simple technique of singularities we can discuss, but before that let us see the arbitrary singularity of Stokes equations. So, let us come to Stokes equation. So, we have the corresponding mass conservation and then the Stokes equation, but not the homogeneous one. We are considering a point source on the right hand side with a strength z bar. Now, we would like to compute the singular solution of this. Okay. So, if you recall in the week 3 we discussed singular solution of Stokes equation, but restricted to irrotational, that is due to potential flow. So, now here we would like to discuss arbitrary singular solution of Stokes equation. Okay. So, there are various techniques to solve this, but we are showing one of the technique. So, replace the delta function by this. Why? Because we know it, we know delta function is nothing but, how do we know? Because for Laplacian, if you consider delta r, we have shown that V is given by some strength by 4 pi 1 over r. Okay. So, therefore, what does it mean? This means delta r is Laplacian of 1 over r. Of course, you can take the corresponding strength. Okay. So, if m is minus 1, what I have written, so we get this. So, therefore, we are replacing delta function by this. Then one option is you set pressure as this and get the corresponding velocity, or we can integrate. Okay. So, I will show you briefly how we are going to get this. Okay. So, once we have the Stokes equation, so this is, let us say, minus g bar by 4 pi delta square 1 by r, because what I have done is replace delta function by the corresponding relation, that is what we have done. Okay. Then we know that, so let us take divergence of that. So, divergence of u is 0. So, we get from here we get divergence of okay. So, now this is constant, g bar is constant. Okay. So, from here what we get is del square p is 1 over 4 pi del square. So, this is, I have used a vector identity, simply you can use this vector identity. So, very straightforward. So, this implies p equals 1 over 4. So, Laplacian, and this is also Laplacian. Okay. Plus a harmonic function, because any harmonic function can be added. From this we are concluding this, right. So, therefore, any harmonic function can be added, but if you see we have for Stokes equation if you combine p is harmonic. So, therefore, any harmonic function we are absorbing. So, therefore, p we are considering it as okay. So, that is how we got the pressure. So, this is a pressure that I have written. Okay. So, there is a minus sign. So, maybe we have taken the wrong side. So, accordingly we got this. So, that is now corresponding to this p, what is the velocity. So, that is the next challenge, right. So, we substitute in the Stokes equation. Okay. So, let us do that. So, this is the P we have. So, now we consider the Stokes equation, which is given by singular Stokes equation, and we have P, therefore, we are substituting okay. So, this plus mu okay. So, this we have gradient operating here and then we have a Laplacian operating here. Okay. So, we can write this as okay. So, this is nothing but the same. I am introducing this is an identity vector. Okay. So, with this we can use. Okay. So, now from here minus 1 over 4 pi gradient we take common. So, this term is this, then this term so we can use okay. So, this what we are doing is this I have taken. So, this is taken to the other side. So, there is a negative sign here and this we have written okay, as it is. So, there should be okay. So, this we have written as it is. So, from here we can adjust So, please note that we are trying to introduce a dyadic notation which is given by this. Okay. So, this is exactly producing the first term and the second term we are writing as it is. Okay. So, you can verify this is equivalent to this. So, where this is a grad on grad. Okay. So, this is called a dyadic notation. Okay. So, from here it is of the form Laplacian operating on u equals to some operator on function of r. Okay. So, this prompts that look for solutions of the form u bar equals some h. Okay. That means, by looking at the structure of this, we are looking for solutions of this form. Okay. So, this is similar to let me explain. Suppose we have an operator L u equals let us say we have r square sin theta. So, let us call Stokes flow past a sphere case a similar structure we have. Then what we are doing? We are looking for solutions of the form f of r sin theta. So, similarly what we are doing? So, we have structure of this form. So, this is the operator on a particular solution. So, here the operator is some operator, therefore, we are taking f. Okay. So, we look for this kind of solution, then substitute in the above equation. Okay. So, then what we get is from these two we can conclude So, that is what we are doing, express the velocity in terms of u, that means we are looking for this. Okay. Then we can substitute in the given equation and observe this will be valid. So, how this is valid? So, we are looking for this kind of solution, I am coming back. So, there will be a mu there. Okay. So, we are looking for such solution. So, then we substitute in the Stokes equation. Okay. So, once we substitute in the Stokes equation, we get del square okay. So, this plus minus this is minus p. So, that is grad p okay, minus I think p was minus. So, this is plus, this is equals so, what is this? This is nothing but, so let me write down, this is del square u term and this is minus grad p term and this is delta. Okay. So, once you substitute in this, then what we are getting is the following. We get from here so this I am excuse me, this is the bracket here. Okay. So, let me write down this equation in a better form, so that we so this was our u, the format of u, that is what we are seeking the solution. Gradient of p equals the delta function. Okay. Now, you can commute, because we are working in Cartesian and this is commuting. So, from here we get del square of h, then these two combining can be expressed in the same operator acting on 1 over r. So, what we get is g dot equal minus g dot on over r. Exactly, we get this by manipulating the vector identity. So, this can be expressed like this, okay, and this already I have indicated dyadic notation, and this we have commute. Okay. So, there will be of course mu there. Okay. So, from here what we get is this operator plus 1 over r equals to 0. Okay. So, that is what exactly we are showing, and this above relation satisfies if we choose del square h equals to minus 1 over 4 pi r. Okay. So, now this is like we have corresponding delta function here. So, this is the Green's function. So, earlier we had a delta function and then we have solved. So, now del square h equal to minus 1 over 4 pi r. Okay. So, this has to be integrated. So, this considering radial symmetry, if we integrate we get h equals to r by 8 pi. Okay. So, this integration is also very straightforward, but maybe corresponding notes will be provided, so that you realize, right. So, this gives the Green's function of a Stokes flow, which means you have potential flow, right, but once we have arbitrary flow, we can get the arbitrary Green's function. So, the moment h is obtained, what is the corresponding velocity? We compute. So, this is the corresponding velocity. So, the h that we have obtained is substituted. Okay. Then we expand. Okay. So, we expand with this, then you realize Laplacian operating on R is 2 by R. So, therefore, the whole thing can be simplified very much, and in index notation we can write u I is this, the same expression, the same u in index notation we can write. Okay. Then we simplify this, we are operating the derivative on R, and then next derivative we are operating on R. So, we try to simplify, and what we get is finally the free space Green's function of Stokes equation. Okay. So, this is in a slightly complicated manner, but this is the arbitrary solution. So, what we are getting is so, this in tensor notation typically we write it. So, where this denotes the tensor, and this particular, so P already we have got. Okay. So, this particular solution is called Stokes-Let. Then similar to the potential case, if you differentiate, the corresponding higher order singular solutions of Stokes law can also be obtained. Okay. So, corresponding to the Stokes-Let, that means, if this is the velocity of the Stokes flow, then the pressure is given by this, stress is given by this, and the vorticity is given by this. Okay. Now, I promised that I will show some application of singularity method. Okay. So, we will consider correspondingly, we will consider the corresponding Stokes flow past a sphere that we have done already. So, let us consider that as an okay. So, let us consider as an application of singularity method Stokes law past a solid stationary sphere. So, what we are considering? A uniform velocity, okay, u bar, and then a sphere of radius r. Our aim is to compute the drag force, which is the Stokes drag. Now, typically in the separable solution, we have shown that we have considered corresponding Stokes stream function and uniform flow, added disturbance, and computed the separable solution, right. So, here in the singularity method, the disturbance will be expanded in terms of singularities. Okay. So, how that is done? The disturbance flow due to the sphere is represented in terms of Stokes-Let and a potential dipole that we have already discussed, which means we are considering the flow is far field is uniform, then a Stokes-Let and a potential dipole. Okay. So, it is slightly the tensor notation etcetera slightly difficult, but this is just to give you an idea. Now, C and D are the strength of the singularity, that means, C bar is the strength of the Stokes-Let, D bar is the strength of the dipole, potential dipole. Okay. So, how do we determine C bar and D bar? Simple, you force the no slip condition. Okay. So, explicit form, this is a Stokes-Let and this is a potential dipole we have already considered. So, now the boundary condition is no slip on the surface of the sphere. So, this would be a nice exercise to understand tensor notation and forcing V I equal to 0 on R equals to capital R, you get these two system of equations, then one can solve for C and D, which means we have determined the corresponding velocity field. Okay. So, as you can see, this is the corresponding Stokeslet and this is corresponding potential dipole, right. And corresponding to this, the corresponding stress operator on Stokeslet and corresponding stress on the potential dipole can be computed, and the corresponding stress on the constant is 0. So, therefore, if we operate this, please recall week 3 lecture, I have computed stress corresponding to potential source. So, similarly, one can compute the stress corresponding to Stokeslet and potential dipole. So, that will be this, and one can integrate the stress 3 by 2 r by considering the surface element on the sphere to know the final result will be the Stokes drag. Okay. So, this is a nice application of corresponding Stokes low pass sphere with the singularity method. Okay. On the other hand, there are lots of other applications of micro particles. For example, if you recall thermocapillary migration of a drop that we have discussed, it also has nice applications. So, we would like to discuss droplets in microfluidic devices. The use is producing calibrated droplets for material science applications. So, that is a big challenge. For various material science applications, you need exactly a droplet of a particular size. Okay. So, in order to speed up some reaction process and to speed up the products to marketing, they require micro droplets as individual nano volume batch reactors. Okay. So, that is very much important application. That means, some micro droplets will be used to trigger the reaction, and hence the application of droplet in various channel configurations are very much useful. So, these are some literature indicating such phenomena, and this is also another literature indicating that phenomena. Okay. So, these are just to give you some insights about various applications, and I hope you get some idea. Of course, understanding the singularity method and the corresponding applications is slightly difficult, but once you spend some time on the tensor notation and understanding singularity of potential flow, one can understand singularity methods and then solve some interesting problems. Okay. Thank you.